In this video, we are going to learn about electrostatics. So, what is electrostatics? Electrostatics means what? Do you know? Does anybody have any idea about what electrostatics means? Now, statics means stationary, like something is stationary. Now, what would be stationary? Of course, charges are stationary. So, charges stationary, and when charges are stationary and we are studying such kinds or such configurations of charges, when charges are not moving, we term that subject electrostatics. Alright? Because why do we impose this condition? Because actually charges are, do we know? I mean, the basic idea of charge or the basic facts about charges are charges comes in two varieties. The first thing is there are positive charges and there are negative charges. Now what happens when these positive and negative charges are near each other? What happens actually? The positive charge and negative charges gets attracted to each other. That is, unlike charges does what? Unlike charges attracts, and like charges repel. Alright. So what it means is if we have a positive charge here and we keep a positive charge close to it, we know that this positive charge will be pushed away from this positive charge. In the same way, if we have a negative charge and a negative charge, in the same way negative charge will be pushed away. But instead, if we have a positive charge and a negative charge, the negative charge will be attracted towards the positive charge. Actually. Okay. So that's something that would happen. So charges are not really stationary in the world that we see around. So we are just concerning a special kind of situation in which the charges are stationary, and then we are going to study it because that subject is more similar. So let's begin. Excuse me. So charges are stationary. So when charges are stationary, something beautiful happens. Like no, nothing beautiful happens actually. When charges are moving, we will see it later. It gives rise to a new phenomenon called magnetism. Magnetism is something is basically magnetism has been initially studied from what? By studying the magnetic materials. Like there has been a story of some shepherd who is carrying his stick and some rock, and that rock attracts the stick or something like that. I'm not really very sure whether this has happened or not, but yeah, and that ore has also has a name. I don't know, like magnetite, or I'm not sure. But yeah, there are stories and anecdotes of these things. But the basic idea is that there are things which has got magnetic properties. That is, materials that attracts each other. Alright? Or some kind of, we have all played with magnets, bar magnets, things like that in our lower classes also. Actually, this lecture is basically designed for a +2, like 12th standard kids. So, but anybody can watch these lectures. That's appropriate. That's completely fine. And so what's next? So this is, and so when charges are like attracting each other, or charges are just there. When charges are attracting or repelling, and charges are at rest. Now, how can we make a charge at rest? So let's think about that for a minute. Like we are now, I am saying charges are at rest, but what does that mean? Like how do we make a charge at rest? So we make a charge at rest by basically fixing it somewhere, like holding it in by some other force. So how do we hold? Let us, for example, let us say if there is a positive charge here, and here there is another positive charge. Okay, so obviously the properties of charges or electric forces will basically push this charge away, or okay, and push this charge away too. So to hold this in place, we need external forces. So we are providing a kind of support, or some other external forces are there which holds it in place. Now we don't need to worry about what those forces are. So that's the beauty of electrostatics. It's somehow kept there. Okay. So when it's just there, then what is going to happen? So that's something that we need to study about. Okay. When the charge is kept stationary, what all properties does it have? Actually, nothing. This uh, the first thing that we have to study in electrostatics is Coulomb's law. Okay, Coulomb is a unit. Coulomb is uh, uh, I'm not very sure. I would need to look it up because yeah, you can look it up. Like what Coulomb is all about is all something that we can just look at some kind of detail. These are all just details, and we can be aware of it. Now we can just search, and we can find out. Even I don't know the exact value of a coulomb in other units, but that all can be learned. That all can be learned by anybody. Like what a one coulomb is, or what a joule is. There is no meaning to all of this. There is meaning. I'm not saying magnitudes matter, but they are something. And this was what Albert Einstein has also said about learning anything. That is, there is no need of learning something or memorizing something that we can really find somewhere else. But now then you might ask me, when everything can be found somewhere else, right? Yeah, actually yes, everything can be found somewhere else. So you just need to study what interests you, and you can use this reason for talking other people into it, like convincing other people. Okay, if I am, I only want to study what I want. So anything that's not interesting to me, can be said they are just facts. They can be learned from anywhere else. So that's something that they can do. So we were talking about Coulomb's law. Now what is Coulomb's law? Coulomb's law basically says that there is an inverse square force. It's an inverse square law. Inverse square law basically means that the force varies inversely as distance squared. That's the force. Now there is another kind of force that has the same property, and that force is gravitational force, right? Gravitational force. And so Coulomb force is basically we can write as F Coulomb is equal to some constant K into Q1 Q2 by R squared. Now this Q1 and Q2 are basically the charges involved. So what is this Coulomb force? This Coulomb force is basically the force between two charges, 2-point charges. Okay, force between 2-point charges. That's what we call a Coulomb's. Now Q1 and Q2 comes with sign. These are not just magnitudes. So this comes with sign, and that sign basically denotes the direction of this vector. Okay. So in more formally, what we need to write Coulomb's law as is basically like this. Coulomb's law is basically talking about a force, which is a vector. And so we need vector notation, right? To make it very precise, we need vector notation. That's Coulomb force Fc is equal to K into Q1 Q2 by R squared R cap. Now what is this R cap? R cap is basically there is Q1 here and there is Q2 here. Alright. Now this force is basically acting on 2 due to what? That is the force on the charge Q2 due to Q1 is where. So that's what we are going to talk about. Okay. And this is the R. Now R is the vector joining what? R is the vector joining Q1 to Q2. And the modulus of this vector is modulus of R, that's R. And this unit vector in this direction is R cap. Alright. So let's just guess. So the force of 2 due to 1 is written in this form. Then what happens is, now if Q1 and Q2 is both positive, let's say if this is positive and this is positive, then what would happen? Then what's the force that Q2 would feel? Q2 would feel a repelling force, which means it's in the direction of R cap. and that's what will turn out here. Positive, positive, q1 is positive, q2 is positive. So this whole thing, k is obviously positive and r squared is positive because r is positive and anything squared is also positive. So k q1 q2 by r squared is positive, which means force 2 1 is in the direction of r cap in this direction, which basically means that it is a repelling force. Now let us assume that one is positive, sorry, one is positive and the other is negative. Then what would happen is q1 q2 would be negative, so this is negative, so this force would be negative r cap direction, which means in this direction. Okay, which means it's an attractive force. And in the same way, if both are negative or things like that, you can easily find out that both would be negative and this whole force would be positive, and it would be in the direction of r cap, which is a repelling force. Okay, so I think those are clear. So let's move on. Okay. And the first thing that we need to learn next is basically Gauss's law. Oh. What is Gauss's law? Gauss's law is basically related to the flux of an electric field. Now it's basically written like this: curve integral E dot ds is equal to rho by epsilon. No, like yeah. And this is Gauss's law. Okay. Gauss's law. So actually, no, I mean, yeah, here this is Q, this is charge. Now, what it's talking about is basically, this is a law. This is a mathematical law. I'm not going into derivation and things like that. But what it really happens is, what is, okay, I will explain what this means. So what it happens, epsilon naught is basically a constant, okay? Epsilon naught, its value we actually need. It's epsilon naught's value, okay, epsilon naught is basically what? Epsilon naught is 8.11 into 10 raised to like something like that. Okay, even I'm not very, I'm very bad at units, so it's 8.85 into 10 raised to minus 12 farad per meter. Okay, so Google Baba comes to help in all these kinds of circumstances, and God has left this place. Now it's farad per meter, yeah, farad per meter, farad per meter. Okay, so 8.85 into 10 raised to minus 12 is basically the unit of what? Epsilon naught. Okay. Q is basically the charge enclosed. So what would you mean the charge enclosed? Okay, let's explain what it really means. Now, things are like, this is assume this is a ball. This is a three-dimensional thing. Okay, this thing is a ball. Okay, and inside this ball we have a charge. Okay, this is a charge. Okay. Now this charge would have, all right. Okay, so first of all, before going into Gauss's law, okay, my bad. I mean, I should talk about what an electric field actually is. So I think I have gone way too far. Like, let me explain what an electric field means. Okay, electric field. Now, electric field is what? Electric field is basically it is physically real. That is, when we place a positive charge in space, the space that is surrounding it has got a particular property that if another charge is there, it would feel a force, and this area, this region is now thought of as a field. Like, this field is basically something that communicates between the charges, that is to move and things like that. And most theories that we see now are basically field theories. Now even gravitation is basically a field theory, and electrostatics and electromagnetics is also called classical field theory. That is, it's really a theory of fields. So what happens is, there is something that's surrounding these matter, the space is surrounded by something that basically pushes and pulls these things. Okay, so now the force that is felt by this object is basically, as we have seen earlier, by Coulomb's law, k q1 q2 by r square. Alright, but it has a dependence on the charge q2, and it has also a dependence on charge q1. Alright, so all the dependence and the constants, if we take it together and we write this is the thing that is dependent on q1, right? So this is something that is independent of q2. If we assume something like that, then we can also view it as F is equal to q2 into E, where E is the electric field. Now this E is only a quantity that depends on charge 1. Alright, it has no dependence on charge 2. Okay, so we can say something independently exists only due to charge 1, and that is basically what we call a field. Okay, so it's mathematical. If you really ask, it's quite confusing, the subject of fields, but it's how we it's how it turns out that it's the most successful theory. Like, it explains a lot of things. So when we partition these things out, one due to the charge q2 and the other due to the charge q1, and this we call field. Now it's better to think of it this way, and it's also very beautiful, right? So there is a body with a charge, and that creates a field around it. And when we place something else in this field, it feels that force. Okay, so we can imagine something. It's a visually nice representation. And Michael Faraday, I think Michael Faraday was the one who really presented this kind of field concept. And they also talk about field lines. Now, field lines. Field lines are basically force field lines. Now, these field lines, this electric field would also have what we call a vector representation, like a pointy head in the direction in which the force is felt. Alright, and electric field can be thought of as a vector. So, because force is a vector, this electric field is also a vector. Okay, so what it means is that this will have a magnitude and a direction, and also it means that electric field. Okay, next please. So this electric field it itself has got different representations. Like, electric field can be thought of as a vector, in which the electric field is only dependent on one charge, that is the source charge we call it. Here in the previous example, Q1 is the source charge and Q2 is the test charge. So test charge is basically used for detecting the presence of a field, and the source charge is basically what produces the field. So these are all technical terms. So electric field is a vector, and we can think of it as Q1 by R square, R cap itself. Okay. So basically what happens, if Q1 is positive, then the electric field would be in one direction, in the positive direction. And if it is a spherically symmetric field means it's the same all around. That is, at a particular radius, if you are going to draw a sphere, it is going to be same at all of those points, which is true because it only depends on the value of r. If r is changing, then E is changing, but at a fixed r, E only has one value. Okay, so that's what we call a spherically symmetric field. Okay, so that property is there. So this is the field lines of this we call field vectors. This is a representation of vectors. And now vectors, this indication has a definite. These vectors are not known to scale. That is, the length of this vector and the length of this vector is the same. Okay, but I don't know how to draw it here, so I am just using it here. I hope you understand. So these are all crucial things. So this lecture is not. This is more like a podcast. Like I am just putting out all the ideas and things that I have, so that it might be quite convenient for a fellow being to understand. So that's why I'm doing this. I'm just ranting out all the information that I have. I'm just putting it all out in a very non-linear fashion, in a chaotic way. So this podcast is meant to be chaotic. So if it's yeah, so these two lines are having the same length, all right. And so then, okay, so this is the magnitude of the electric field, right? So how will this change? This will change like r squared, like inverse of r squared. So if this is the r, along this is a particular r, in this field, this decreases with r squared. That's what it means by 1 by r squared. So if r is increased, this is r1, okay, let us assume. And from the source charge, this is r2, okay. So at r1, it's kq1 by, now here the electric field would be, if it has having this much length, in a sphere that is drawn about this point. You see, this is a sphere, okay. Unfortunately, this is a sphere. It is not a sphere, but let us assume this is. This is a sphere. This curved line, this dashed lines are basically a sphere. In all of those points inside that sphere. Okay, I think I can draw a sphere. Like, no, I can't. No, sorry. Oh, sorry. I can't. I can't draw a sphere. So, what I'm saying is, so in this point, all of the distances that is in the sphere, there is a sphere, and in all of these points inside in that sphere, in that spherical surface, the electric field has got the same value, and that is kq1 by r square. Now if we draw another sphere at another distance, that is at r2, we draw another sphere. Okay, this is another sphere. Okay, sorry, this is a sphere. In this sphere, what happens is uh, it would have a different value, and that would be less because r2 is greater than r1. Okay, so if we draw this much length vector here we can't draw this much length vector. Here we should draw a small vector. Like if we draw a vector like this here, we should draw a vector like this here. What it means is, over these points the vector is shorter, and over these points the vector is large. I hope I understand. Okay. So and there is another kind of representation, and that's the representation of electric field lines. And the electric field lines, what happens is, all of these vectors can be connected together. Okay? Connected together. So what happens is, there is a vector here, there is a vector here, there is a vector here. Now all of these things can be connected together as a single line, and this line is called electric field line. Okay. Now you have seen maybe a lot of patterns of field lines like this and this. Now field lines of dipoles like plus and minus. Field lines of dipoles like this. There's a lot of dipoles. Or things like positive charge with repel. Field lines of dipoles like this. Right. And there is an indication. Okay, this is a positive charge, so there is an arrow. But the strength of the field lines information has been gone actually. Right? But it turns out that the field lines, when they are closer together, it is more strengthened than when it's farther apart. Like if you take a small area over here, okay? Let me take a small area over here. If I have say if I have let me draw it like this. This is how field lines behave. Now if we take the same area over here, as we can see, how many lines have passed through this area? Let us say some 5 lines have passed through this area. Only 4 lines would have passed through the same area at a distance. Okay, I hope the idea is clear. And so the number of lines passing per unit area is basically an indication of how strong the field is. So the field is stronger here, stronger than here. Weaker. Not here, it's weaker. Okay. Okay, so there are such things. So field is stronger nearby charges and field is weaker when field lines are sparsely located. Like the density of field lines crossing a unit area or the number of field lines that is crossing a unit area is basically also called flux. Like per unit area, how much field lines are entering or leaving, like how much field lines are present, how much field lines are present is also termed as flux or electric flux. Okay. Electric flux. Now electric flux mathematically is represented by phi. Phi is equal to what? E integral E dot ds. Now this phi is basically through a closed surface, okay, but in differential form through a very small area. Well, this is a particular area, and this area, I think you have been seen areas as vectors. Like area also has something called a vector, like an area element. Let us say this area, the area of this thing is ds. Then it also has an arrow pointing in either of this direction. It could be in this direction or it could be in this direction. We can choose one direction and denote that vector or unit vector by r, and then this thing, this area could be treated as a vector, and that is ds. Okay. Okay. And electric field is also a vector. Okay. So let's go to the first description of electric fields as vectors. So electric fields are also vectors. Now electric field dot ds basically talks about what does that mean is modulus of E modulus of ds cos theta. This is what we mathematically term to be the electric flux. Now let us we have an area like this, and the area is having a direction like that, and the electric field that passes through here is basically having a direction like this. Okay. Okay. When the area is perpendicular, that the area vector is perpendicular to the electric field, actually no electric field is passing the area, so the flux is zero. And if the area and the electric field is aligned in the same direction, that is, then what we mean is that all of the electric field is passing through the area. Okay. Okay. So that's it. So that's the idea of flux. Okay. And this integral basically means that we are talking about a curved surface over the surface. Let us say closed surface. So now this circle in the integral means that we are integrating this fluxes, small fluxes over all the small parts of areas. This is a very big surface. This is a small area. Now the flux in this area is calculated. There is another small area over here. The flux in this area is calculated. Another small area here. The flux in this area is calculated. We add them all up, and we get the total flux that is passing through this whole surface, closed surface, and that we denote by curved, closed integral over S. S is the surface. E dot ds. E dot ds is basically also written as d phi. Okay. E dot ds is d phi. So small flux through an infinitesimal area. So the flux through the whole area is just this. Okay. Closed integral of S E dot ds. Now we have seen this somewhere else, right? We have seen this thing in losses here. So now you might have a Now you might have like something something nice, or now you might have a better idea of gauzes. Maybe you don't have it. So what Gauss's law states is that the curved integral over a surface E dot ds. It's a total flux through a closed surface. Closed surface basically means surfaces like closed surface means surfaces which are closed, like a sphere, a ball, a hollow ball, take for example. And inside a hollow ball we can place things, okay? But the surface is closed. An open surface will be something like this. This is an open surface. Right? This is just there. This is not closed. We can't place anything inside the surface. Like, it's not curving in on itself. Right? Such surfaces are called closed surfaces. And even this is something. This is an open surface. But we can make it a closed surface by closing it. Like all the there should be an interior space for the surface. I would be maybe explore. Now let's so now this is a thing, okay? This contains sketches. There is a small opening here, I leave it. But if we cover this opening and we take all those sketches out and we just keep it like this is a closed surface. It has an interior space, okay? Where we can place things. So that's why it's a closed surface. So we are integrating this flux over a closed surface, and what happens is that integral of E dot ds over S is equal to what? Is equal to Q by epsilon naught, and this Q is Q enclosed. What does that mean? Q enclosed. Q enclosed means, that's why I said we need to keep something inside. We need to keep something inside. And we assume that the charge is placed inside this. Then Gauss's law connects the flux through the surface and the charge magnitude that is present inside it. Now there might be charges that are present. This is a charge that is this charge is present here. Now there are charges all around this body, and there are charges inside this body. And what happens because of Gauss's law is the flux through the surface is only dependent on the charges inside this body. It's not dependent on the charges present outside the body. So this is a law, and this law is completely mathematical. I don't know how to prove it. If anybody needs a proof of Gauss's law, I would very well look it up and provide to you here itself. So I think I should wind up this class. If you like this and you need more of these kinds of like podcast type videos, like this and share this with your friends, and yeah, do all of those stuff. All the YouTubers also do. And, yeah, and like this video, share this video, subscribe to my YouTube channel. Yeah, do all of these things. Bye. So let's see soon. With we continue. There are a lot of topics to deal with, as I will continue. Okay. Okay. Bye.